An engineer needs to measure the minor loss coefficient of a reducing elbow which has already been installed in a piping system. Because of limited access to the piping system, the only available pressure taps are 1 meter upstream and 0.75 meters downstream of the elbow. A mercury manometer is attached at these locations and reads 7.5 centimeters of mercury when the mass flow rate is 1 kilogram per second. What is the minor loss coefficient for the elbow? Assume that all pipes are smooth. The flowing liquid is water with a density of 1,000 kilograms per cubic meter and a dynamic viscosity of 0.001 Pascal seconds. So we're also given a sketch of this apparatus. So here's the reducing elbow that we're trying to figure the minor loss coefficient of. The input to that reducing elbow is a vertical section of pipe. We can tell it's vertical because we're given the orientation of G over here. And that vertical section of pipe is 1 meter long and has 4 centimeter diameter. The pipe diameter reduces through this elbow and then goes on for a further 0.75 meters horizontally, and that's a 2 centimeter diameter pipe. Now at this location and at this location, the mercury manometer is attached, and the mercury is down here, and the manometer deflection is 7.5 centimeters. And as we were told in the problem statement, there's 1 kilogram per second going through this. So we might as well use this diagram as our given information. We'll probably be adding a few things to it as we go along. We'll come back and do that. First of all, identify what we're asked to find. And go back to the problem statement. We're asked to find what is the minor loss coefficient for this elbow. So that's what we're after. So we're after K of the elbow, the minor loss coefficient. Assumptions. We'll keep track of those as we go along, and we'll begin the analysis. So we go back to our diagram here and take a look. The location of these pressure taps is important because we know information at those 2 points. The mercury manometer is going to tell us what the pressure difference is from there to there. So we're going to be writing Bernoulli's equation through this piping system from this location to that location. So we're going to label this as point 1 and this as point 2. And we'll write Bernoulli's equation between those 2 points. Now the reason we're writing Bernoulli's equation with losses between those 2 points is we know that this elbow is a minor loss, and it'll show up as one of the contributions to the pressure drop going through there. So start off with Bernoulli's equation and see where that takes us. So from point 1 we go P1 plus rho V1 squared over 2 plus rho G Z1 has to equal P2 plus rho V2 squared over 2 plus rho G Z2. So that's the basic Bernoulli's equation. But of course here we're going to take into account the losses as well. So there's summation of FL over D rho V squared over 2. So that's the frictional losses in the pipe. And notice I have a summation here because there's more than one pipe. There's a large one and a small one. And in addition to the friction losses, there's also the minor loss for the elbow. I'll just call that KE, and that's also multiplied by rho V squared over 2. So notice this is our unknown in the problem, the minor loss coefficient of this elbow. So as long as we can figure out all the rest of this stuff, then we can get that minor loss coefficient. So let's take a look at what we know and what we don't know in this equation. And we go back to our diagram. Realize that we know the mass flow rate and we know the diameter of these 2 pipes. Okay? So we go back to Bernoulli's equation. These velocities then we know, or we can figure them out because we know the mass flow rate and we know the diameter. So that we can get, and this we can get. We certainly need to keep them in the equation, but they don't pose a problem because we know them. Z1 and Z2 we know the dimensions, or we know how far point 2 is above point 1. So those two we can get. Again, the frictional losses shouldn't pose a problem because we know the flow rate. So we can get a Reynolds number and a friction factor, and we know the velocity, length, and diameter of each of those sections. So we'll have to figure all that stuff out, but it shouldn't pose a problem. The minor loss coefficient, again, is what we're after. And again, we know the velocity. We should go back and make sure we have the assumptions that go along with Bernoulli's equation. So that assumes that we have steady flow. It assumes uniform flow in the pipes. So we're just representing with a single velocity. It's incompressible. Temperature is constant. And there's no heat transfer. And there's also no work transfer because there's no pump anywhere between point 1 and 2. Okay. The other thing that we're going to be saying here that I might as well get down in that assumption list right away is notice that this distance here is 1 meter. And we really don't know the size of this elbow, so we don't really know the additional elevation up to point 2 here. So I'm just going to assume that this distance is very small compared to 1 meter. So the way that I'll write that is there's no, or the elevation change between point 1 and point 2 is just the 1 meter. So we'll put that in our assumption list here too. So negligible elevation change in the elbow. And that means that Z2 minus Z1 is 1 meter when we get to that point. So we're going to do some rearranging of the terms in Bernoulli's equation here to help us solve it. So I want to bring these pressures both to the same side. So I'm going to go P1 minus P2, and we're going to show how to get P1 minus P2 in a few moments. We're going to be using the manometer to figure out what that is. And I'm going to put everything else over on the other side. So the kinetic energy term at point 1 will become minus rho V1 squared over 2. But notice in pipe 1, there's also going to be some frictional losses. So I'll put plus FL1 over D1, and that's in pipe 1. That's what the subscript 1 is for, times rho V1 squared over 2, because it's got to be based on the velocity in pipe 1. The elevation term I'm also going to take over to the other side. So we'll have there plus rho G Z2. So that's this part. And then minus Z1. That's this part moved over to the other side. So I've got my two pressures taken care of. I've got this kinetic energy term taken care of. I've got the elevation terms brought down here. So I still have this kinetic energy, so that's plus rho V2 squared over 2. Then I've got to remember the frictional losses in the smaller pipe. So that's plus FL2 over D2, rho V2 squared over 2. So that's the frictional loss in the small pipe. And then finally, the minor losses. And I'm going to choose here to base these minor losses on the velocity in the small pipe. So I put V2 squared over 2 here, rho V2 squared over 2. Notice that when we finally calculate a number for this minor loss coefficient, we have to specify, along with that number, it's part of the answer, that it was calculated based on the velocity at the exit of the reducing fitting. If we wanted, we could put V1 here, and we would just have to state that that minor loss coefficient was based on the inlet. so that when somebody goes to use this minor loss coefficient, they know which velocity to base it on. So we can clean up the right-hand side of this equation a little bit. You'll notice that we have two terms here with rho v1 squared over 2 in them, so we'll be factoring that out. And we have three terms here with rho v2 squared over 2. So our pressure difference, put over here, I'll just say rho v1 squared over 2. So here we have FL over D, so that's that part, minus 1. And that's all in pipe 1. Plus something very similar in pipe 2. I'm just going to do this part next. So rho v2 squared over 2. Our frictional losses, FL over D. Our kinetic energy term, which is just 1, plus this exit loss coefficient. And that's all for pipe 2. And then we also have our elevation change, plus rho g z2 minus z1. So remember here, that's what we're trying to find. And actually everything else on the right-hand side, at least, except for this, we can actually get relatively easily. We don't have friction factors or velocities yet, but we know enough information to calculate those. The issue we have with this, though, is this pressure difference. We don't know what that pressure difference is at this stage. So what I'm going to do is set Bernoulli's equation aside for a moment here and focus on the left-hand side of this equation. So we need to find this pressure difference. And the way we're going to do it is by taking a look at this manometer. So like we did when we did manometer problems near the beginning of the course, the way we do it is we go from this point to that point through the manometer. And every time we see the fluid change, so here it's changing from water to mercury, we label the point. Continue on, still mercury. This point here, changing from mercury back to water. And then, of course, the rest of the way, it's water. So the very first step of the manometer problem is to represent this pressure difference as the sum of that pressure difference plus this pressure difference plus that pressure difference. So that's our first step down here. So we're going to set this aside for a moment, and we're going to say that P1 minus P2, but looking at the manometer problem now, that must be equal to P1 minus PA, and that's in water, plus PA minus PB, that's in mercury, plus PB minus P2. So the total pressure difference is the sum of those three steps. Now, where do these three individual pressure differences come? That's where the basic hydrostatic equation comes in. So if I'm going to use the basic hydrostatic equation, I have to say that manometer fluids not the fluid in the pipes, but the fluid in the manometer tubes. So the manometer fluids are hydrostatic. So that lets me use the basic hydrostatic equation in the manometers. There's no acceleration because this thing presumably isn't flying around. G, I'm going to say, is equal to minus GK. So you'll notice that in the diagram we have G pointing downwards here. Well, because we've already used Bernoulli's equation, Z has to be pointing straight up because the potential energy term in Bernoulli's equation is being represented by Z. So G is equal to minus GK, so dP dZ is equal to minus rho G. And so we integrate that, and we can integrate it between any 2 points in the same fluid. It has to be in the same fluid because we're going to treat density as a constant. So any 2 points, PB minus PA, will be equal to minus rho G ZB minus ZA. So B minus A here, B minus A there. So this equation we can use, substitute it in here 3 times, and represent these pressure changes by density times G times elevation changes. So that's what we'll do. P1 minus P2 then is equal to minus rho, and this first portion is in water, so we'll say density of water times G times Z1 minus ZA. So notice it's P1 minus PA, so here it's Z1 minus ZA, same order. Then minus rho of mercury times G, ZA minus ZB. Finally, minus rho of water again times G, ZB minus Z2. Now we want to go back to the diagram and just see what these elevation changes are. So we're going to be rewriting this again, but we'll write these elevation changes in terms of the dimensions on the diagram. So this is minus rho water G. Now we'll go back to the diagram. We're going to be looking at Z1 minus ZA. So this is Z1 minus ZA. So there's 2 parts to that. There's this manometer deflection of 7.5 centimeters, and I'm going to let that equal H, because I just want to call it H as I work through rather than substituting in the number and its units right away. So that distance is H, and I'm going to call this distance L. So we'll call that L. We'll just temporarily label that L. So Z1 minus ZA is going to be L plus H. So we can go down and put that in. So this is L plus H. So minus rho of mercury times G. Now we got to look at ZA minus ZB. So ZA minus ZB, notice ZB is bigger than ZA, higher up. So ZA minus ZB is negative H. So negative H. So that's that one. And then minus rho water times G, ZB minus Z2. Go back up to our diagram. So that is this Z minus this Z. So that's going to be negative L minus Z2 minus Z1. Go back here. So negative L minus Z2 minus Z1. So this is our pressure difference, P1 minus P2, written in terms of density G and the dimensions labeled on the manometer. Now we can clean this up quite a bit. Now take a look at this. We have here a minus rho water GL. And over here we have rho water GL, but it's positive because that negative times that negative is positive. So this cancels with this. So notice what's happened here. There's no longer an L in this expression. So if we go back to our diagram, it means it doesn't matter what this L is. And that's true because as we travel from here down to here, the pressure increases. And as we travel from here up to here, it decreases by the same amount. So it doesn't matter how long this portion of the manometer is. This deflection is going to be the same for a given pressure change between 1 and 2. So that L has canceled out of our expression, and that makes sense. So I'm going to combine these 2 terms together now. So I'll put rho water times G times H times the specific gravity of mercury minus 1. So that is the same as these 2 terms combined together. So notice negative times negative is positive, and this is mercury. So that's where this positive specific gravity of mercury comes because I factored out density of water. And then this term here is minus rho water GH, and that's this, minus 1 here, minus rho water GH. So these terms are represented by that. And for this, we just have plus rho water times G Z2 minus Z1. Notice this negative and that negative become positive. So now we've done the manometer problem and we've got an expression for P1 minus P2. So we can combine these together. Go back to our Bernoulli's equation. Remember we have this. P1 minus P2. We now have another expression for it in terms of the manometer deflections. Before I rewrite these, notice this P1 minus P2 has a rho water G Z2 minus Z1 in it. And this one also has a rho G Z2 minus Z1. All of the densities in this are densities of water. So this term on the right-hand side of Bernoulli's equation is going to cancel with this term when I substitute this in. So I'm going to just get rid of those two right away. So I'll rewrite this on the left-hand side, rho GH, and this rho is a rho of water. I'm going to drop this subscript because in Bernoulli's equation they're all at density of water. So rho GH, specific gravity of mercury, minus 1. So that's now the left-hand side of this equation, with the rho GZ2 canceled off with this term already. And the right-hand side, what's left is our rho V1 squared over 2 times FL over D for pipe 1 minus 1. That's all for pipe 1. And then plus our rho V2 squared over 2 times FL over D plus 1 plus K of our elbow, and that's all for pipe 2. So just go back and remind ourselves where that's coming from. So that's these terms here that I'm just rewriting. So the P1 minus P2 from the manometer and the rest from Bernoulli's equation. So remember, that's what we're after. So we're in good shape now. We need to just figure out numbers for some of these things that go in there. So let's start with this velocity. So V1, the velocity in pipe 1, is going to be the mass flow rate in pipe 1 divided by the density times area 1. And that mass flow rate is 1 kilogram per second. And the density is 1,000 kilogram per meter cubed. And the area is going to be pi by 4 times the diameter squared. And the diameter is 0.04 meters. And that'll be squared. And we calculate this out, and it comes out to 0.7958 meters per second. We do the same thing in pipe 2. So that's the mass flow rate divided by density and area 2. And pipe 2 is smaller, so this velocity should be coming out quite a bit higher. So same mass flow rate, assuming no leaks, I guess. Same density, 1,000 kilograms per meter cubed. Pi by 4. But now our diameter is 2 centimeters, so 0.02 meters. So remember to use standard SI units for everything here. And this works out to 3.183 meters per second. So notice quite a bit higher velocity because the smaller pipe diameter. As a matter of fact, half the diameter, therefore 1/4 the area, therefore 4 times the velocity. Could have actually calculated this velocity very quickly from this one just by multiplying by 4, but no big deal. So we have the two velocities. So we take stock of what we know and what we don't know. Density we know, G we know, H we know, specific gravity we know, so everything on there we know. We figured out this velocity, figured out that one. The only thing left here are these two friction factors. Notice they're different because the Reynolds number is different, so we have to calculate those two Reynolds numbers. So the Reynolds number in pipe 1 is going to be equal to density V1 D1 over mu. So that's 1,000 kilogram per meter cubed is our density. V1 we just figured out, 0.7958 meters per second, and D1 is 4 centimeters, so 0.04 meters. And the dynamic viscosity, 0.001 Pascal seconds, which was given in the problem statement. So Reynolds number 1 works out to 31,831. Same thing for Reynolds number 2. Density V2 D2 divided by mu. Density 1,000. Velocity much higher. That's our 3.183 meters per second, and diameter smaller, 0.02 meters. Viscosity the same. So that gives us a Reynolds number of 63,662. So we have the two Reynolds numbers, so we can go to the Colebrook equation and get our two friction factors. And if you remember, the problem statement said that the pipes were smooth, so we're going to be setting epsilon equal to 0 for both of these pipes. So we say epsilon 0, take these two Reynolds numbers, and we get a friction factor of 0.02316 for pipe 1, and a friction factor of 0.01981 in pipe 2. So we now have everything we need. So everything in this thing is known now except this Ke. So we can substitute all that stuff in there. So if we calculate Ke from that equation, it works out to be 0.108. And remember, part of this answer is saying that that's based on the exit velocity.